everybody, Dr. Jim Daly here. We're streaming live from Argentina, courtesy of Reuters. This is a total eclipse of the sun. We're in the partial phases where the moon in its new phase is halfway across the sun's disk. Geometrically, the moon is 400 times smaller than the sun, but 400 times closer. So it's a geometric perfect fit on the face of the sun. So this is a map. The path of the eclipse, the path of totality, is identified by this brown line here. There's Argentina. There's Chile. Obviously, there's a filter in front of the camera. The sun is even half covered by the moon, such as this. The sun is still going to be enormously bright. You will notice some dimming of the daylight, but the sun will be still quite bright. You're going to need a filter until just before the full eclipse starts, totality starts. Then you're going to need then you remove the filter and you let the true grandeur of the eclipse come through. This live stream is courtesy of Reuters, news agency, stationed in Latin America along the path of totality, somewhere along here. Here's Chile, here's Argentina. Now, typically the path of the eclipse, the path of totality, which is this path here, this is the projection of the moon's shadow onto the surface of the Earth. This path is generally about 100 kilometers wide. So the line, anybody that's located inside that path will see the eclipse, the total aspect of the eclipse. Anybody outside of these boundaries will only see a partial eclipse. Okay, the center line, what we call the center line, is this brown line. So if you station right on that line, you're going to see the full eclipse for its entire duration. If you're outside of this line, but within the blue boundaries, you're going to see the total eclipse, but for less time than it would have been had you been on the center line. Okay? The sun looks very quiet, meaning you can see the solar granulation and the limb darkening. The limb darkening is basically when you're looking into deeper sections of the sun's atmosphere. The sun is not a solid surface. It's a superheated ball of plasma about 1.5 million kilometers in diameter, 700,000 kilometers in radius. Okay, so when you look along the limb of the sun, the edge of the sun, you're looking into lower depths of the sun's atmosphere because you're looking at an oblique angle. Okay, so that's why you see, that's what creates this effect here. They call limb darkening. The region of the sun looks darker along the rim. And there are no sunspots visible. The sunspots are basically breaches in the sun's, the transition of energy from the depths of the sun to the surface, which we call the photosphere. When those breaches occur through magnetic field lines that interrupt the flow of energy, we get sunspots. We see sunspots where that particular region is a little bit cooler than the surrounding area, looks darker, but it's still enormously hot. It's about 30 minutes till we have the full totality. Okay, so the eclipse is currently in progress. Okay, if we look at a large-scale map of the southern hemisphere, that's the shadow of the moon. Let's repeat that again. Okay, so we're going to pause it. I'll explain to you what this means. This is the umbra. This is the path. This is the, if you're in this circle, it's about 100-kilometer radius, 100-kilometer diameter rather. That's where you're going to see the full total eclipse. This is the umbra, and this larger shadow here is what we call the penumbra. Okay, and so if you are stationed along the path identified right here, you're going to get to see the total eclipse of the sun. Okay. This live feed is courtesy of Reuters, on location, on site in South America. Now, it should be pointed out that the moon is moving at about 1 kilometer per second in its orbit around the Earth. Okay, and as the Earth turns below it, okay, the shadow then will appear to move along the surface of the Earth at about 1 kilometer per second in its orbit, in its movement along the surface of the Earth. The shadow will basically move at the orbital speed of the moon, which is about 1 kilometer per second in its orbit, a little bit more than 1 kilometer per second. Okay. And in some cases, and I'm not entirely sure in this case, if they have observation planes that fly aloft and chase the moon's shadow across the surface of the Earth. At least at the cruising speed for an airliner is approaching 600 miles, is approaching 960 kilometers an hour. Mach 1 is about 330 meters per second, which is 0.3 kilometers per second. Okay, so if at that speed, it's just 1/3 the orbital speed of the moon. So just a quick calculation, the order of magnitude calculation. A jet airliner, the cruising speed at altitude of a jet airliner, you'll be able to extend the duration of totality by a considerable amount. It's about 1/3 of the orbital speed of the moon. The jet cruises at about 960 kilometers an hour, which is about 1/3 the speed of sound. Well, excuse me, it's just shy of the speed of sound, which is 330 meters per second. So you'll be able to considerably extend the duration of totality on the, for you as an observer on the jet plane, on the airliner. So the times and the time and date information here. This is universal time. This is UTC, which is if you're on the eastern seaboard. First contact is at 8:35 in the morning. This is New York time. (12:54) and 1:53 p.m. just to see the last aspects of the eclipse end. Okay. Maximum eclipse, which means totality, if you're on the path of totality, which is slightly before 11:15 in the morning, which is 1600 UT, universal time. So this is where we're looking right now, right across here. Here's the Malvinas Islands down here, territorial islands of Argentina. Down here, get a sense of where the path of totality is. This dark line here is the path of totality. It ends just off the west coast of Africa here. Begins out in the middle of the Pacific over here. This is the northern coast of Antarctica here. Okay, so that's where we are, live in South America. Now, while we're watching this, let me just explain quickly what's happening with this, how the sun produces its energy, in case those of you out there who are not sure. The sun produces energy through nuclear fusion, a process that we have been unable so far to actually replicate here on the surface of the Earth. The sun is an enormous, gravitationally bound sphere of superheated plasma. The surface, it's not really a hard surface, we call the photosphere, is about 5,780 degrees Kelvin. Kelvin is a temperature scale that's based on 0 as the absolute temperature scale, where 0 degrees Kelvin is 0 degrees. There's no energy present, so okay, it's at 0 degrees. So Kelvin, the Kelvin scale is based on an absolute concept. All right, so this is 5,780 degrees Kelvin. Internally in the sun, down deep in its core, 700 kilometers below this what they call the atmosphere. The photosphere is it's an aspect of the solar atmosphere. Above the solar photosphere, we have the chromosphere, and then the corona, the superheated outer tenuous regions, hot outer tenuous regions of the sun. Okay? So deep down inside in the core, 1/3 of the, almost all the way down, 1/3 of the solar radius is the size of the core. In that core, temperatures of 15 million degrees, where we have 4 hydrogen nuclei, which we call protons, are combined, are jammed together because they want to repel each other, right? In classical physics, in classical electrodynamics, protons want to repel each other. Opposites attract, likes repel, right? So if you have a like electric charge, 2 positive charges want to repel. Okay, but very powerful, very strong, the tremendous pressure at the in the core of the sun drives these, overcomes the electrostatic Coulomb repulsion, drives them together, and the strong nuclear force grabs them and holds them fast, 100 times more powerful than the tendency to repel. When that happens, we just created a new element. That element we call helium. It has 4 protons, and through a series of nuclear processes, the 4 protons now become 2 protons and 2 neutrons. We release a gamma ray, which is the energy that comes from that reaction, and what we call a neutrino. 2 neutrinos are produced, okay, which takes some of the energy away too. All right, so that's how the sun is producing energy, nuclear fusion. We've yet to replicate that here on the Earth. There are attempts now to try to reproduce that energy, completely carbon neutral, free of any kind of negative effects to the environment and the atmosphere. Nuclear fusion, if produced, or if we're able to technically produce it, or if the technology is developed where we can actually produce it, it will be a boon for mankind, for humanity. We could actually completely move away from fossil fuels, and we can rely on the energy of the sun to produce our energy for us. Okay, we will have entered a whole new era of our stewardship here of the planet Earth. Okay. Now, as you can see, the partial phase of the solar eclipse is starting to come to a close pretty soon. Within about 30 minutes, we're going to have the total phase of the eclipse, where the moon will completely cover the face of the sun, and we're going to start to see the what they call the chromosphere, which is a hot, slightly hotter layer of the sun just above the photosphere. We're going to start to see the ruby reds, the pinks of the chromosphere, and what we call prominences, the giant jets of hydrogen gas that leap off the sun's surface, many tens of thousands of kilometers in size, that just leap off the sun's surface. And we're going to see that in just a short while. So please stay with us, stay tuned. This is Dr. Jim Daly of Astronomy for Change, bringing you the total solar eclipse in Latin America live here at Astronomy for Change. Now, in order to follow the eclipse, because the Earth is rotating, I'm not sure of what kind of equipment they're using. It's most likely a very long range, very long telephoto lens, or perhaps a telescope. Most likely it's a telescope. The telescope has what they call a clock drive. It's a drive that maintains the same the angular rotational speed as the Earth as it turns on its axis, which causes everything to rise and set in the sky. We want to maintain the object of interest. We want to maintain it's centrally located in our frame of view, right? Our field of view. So in order to do that, we have to produce the telescope has to be rotated at exactly the same speed as the Earth is, the angular speed as the Earth is turning. We call that a clock drive, and no doubt they have such equipment set up here to track the eclipse as it continues. This is the observing station. All the observers. You notice how the birds are starting to chirp. This is the flag of Chile. So they're in Chile. This is the flag of Chile. Okay, so we're in Chile. You notice the birds think it's twilight or dawn, so they're starting to, produce their calls that they would normally produce at the end of the day or the beginning of the day. The birds think this is the change of the day, the setting of the sun or the rising of the sun. You hear the birds in the background, you can see the subdued light in the region, in the area. So we're in Chile right now. This is the observing station in Chile. Everybody's excited. You can hear them. Well, we're almost at second contact. First contact is when the moon first touches the limb of the sun. Second contact is when the limb of the moon touches the limb of the sun. And we start to see amazing effects such as the diamond ring effect and Daly beads, which is the last vestiges of the sun's light passing through the mountains beyond me while they keep switching back to the crowd. You notice how dark it's getting as the sun is, and you can understand how the ancients became terrified that the sun, the source of all light and heat for the planet, is now being taken away. It's understandable how they could deify the sun as they did. There's a lot of stories in mythology. The Chinese believe that there was a giant dragon taking bites out of the sun. Okay, we're approaching second contact. You can see the Daly beads starting here, right here. We're coming up on second. Here we go. This is totality. Here we are, second contact. They have to remove their filter. They haven't done that yet. Here we go. Maybe they can take their filter away. Oh, and the clouds we're covering. Here we go. Wow, that's amazing. You can see the prominences here. I talked about the prominences, these giant streams of hydrogen gas leaping from the photosphere of the sun. You can see that what we call the coronal streamers here that are formed by the sun's powerful magnetic field. This is an amazing view. This is a fantastic view of the total eclipse of the sun. Live coronal streamers here, live prominences rather. This here is about 10,000 kilometers in height, right here. You could fit the Earth inside this right here. The planet Earth could fit inside this. Here we go. These are the people here on the west coast of Chile. This is in Chile, obviously because of the water. Argentina doesn't border the east coast. Okay, this is third contact. Third contact is where the moon moves off the face of the sun. And fourth contact is when the eclipse ends. So apparently there's some high altitude thin clouds eclipsing the eclipse. That was an amazing view of the sun. So this was on the west coast of Chile, this view of the eclipse. You see the clouds, or in Spanish, the nubes, los nubes, the clouds. Okay, so we just passed third contact. Third contact, an eclipse consists of four contacts. First contact is when the limb of the moon just touches the limb of the sun. Second contact is when the full phase of totality begins. Third contact is when the moon leaves the fully eclipsed sun, which is what we just witnessed now. And fourth contact is when the trailing edge of the moon just leaves the leading edge of the sun. So we can see still, there we go, the clouds have moved away and they replaced the filter on their equipment. This live stream was brought to you courtesy of Reuters News Agency. This is Dr. Jim Daly. We're hosting this live event, bringing to you the total eclipse of the sun as witnessed in Chile, the west coast of Chile. It's interesting to see the reaction of the people. Many of these people perhaps have never seen an eclipse, and this was their first eclipse. For me, my first real eclipse was in 1991 in Cabo San Lucas in Mexico. July 11th, 1991. Beautiful clear sky in Cabo San Lucas. Eclipse de solar. Eclipse de solar. Eclipse solar. Eclipse of the sun. Total eclipse of the sun. It's interesting to listen to the background conversations in Spanish. So what's going to happen now is that thin crescent of the sun will continue to get larger and larger as the moon moves away from the disk of the sun. It's a nice image of the the waning eclipse. Waning meant in this context as well, the waxing limb of the waxing crescent sun getting larger. Waxing used in this context as getting larger. Live event brought to you courtesy of Astronomy for Change. I'm Dr. Jim Daly, your host for today. We just witnessed totality. It was a beautiful, beautiful, beautiful eclipse. And you can get a sense of the sun's activity, what the astronomers refer to as the solar activity. We have maxima and minima. It's generally an 11-year cycle. Every 11 years, the sun goes through these cycles. 11 years, we have a maximum. From maximum to maximum is 11 years. What does that mean? Maximum, sun's maximum is the internal activity of the sun. Now we're in what they call a solar minimum, which also has, it's 11-year cycles. All right, now we're going to be coming out of the solar minimum. We're going to start to, the sun's activity internally will start to increase. That means the internal dynamics of the sun get stronger, more active, and we generally regard this as the solar maxima and minima. Okay. Apparently, we're dealing with an overcast situation here in Chile, but at least we got to see the eclipse. So you can see the overcast conditions they're dealing with there. But fortunately for them, and for us as observers here, overhead was clear. We were able to witness the sun, the eclipse of the sun, and breaks in the clouds. In spite of the pandemic, the resilient Chileanos came out to see the eclipse. The Chilenos, resilient Chilenos, came out to see the eclipse. Arriba Chile, arriba Chile. There's the sun. So we're on our way to fourth contact, where the limb of the moon, which is this, will touch the trailing edge of the moon, will touch the leading edge of the sun, and the eclipse will have ended. That's what we call fourth contact. Second contact is when we're immersed in the total phase of the eclipse. So within that 100-mile swath, 100-mile path along the surface of the Earth, if you're inside that 100 kilometers, here, this is about 100 kilometers wide, you get to see the eclipse. You get to see totality. Okay? Any person here gets to see a partial eclipse. Any person inside this is what they call the umbral shadow. This dark band right here is what we call the umbral shadow. And if you're in that umbral shadow, you get to see a total eclipse of the sun. If you're on that what they call the center line is where you have the full eclipse. You get the maximum amount of time for the eclipse. Outside of this, the dark band into the lighter band, that's the penumbra. The penumbral shadow, you see at partial phase, which is what we've been seeing, which is what is visible now. And outside this region, you see no eclipse at all. I beg your pardon, outside of here you see no eclipse at all. Inside this region here, the lighter shadow here, you get to see a partial eclipse. Okay, the total eclipse you have to be in this dark band here. As I was explaining earlier, the moon is moving in its orbit around 1 kilometer every second. Okay, the speed of sound, which is basically 3 times the speed of sound. The speed of sound at sea level is 330 meters a second. Okay, a kilometer is 3 times that speed, a kilometer every second. So the moon's shadow is moving at about 3 times the speed of sound along the surface of the Earth. So there are many, and they might have, I'm not sure at this point, but there are many who have, colleagues of mine actually have worked on the what they call Eclipse charter flights, where you can, it's modified A320 aircraft. It's modified, allows instrument bays to be deployed inside the aircraft, and they can fly at cruising speed, which is basically about 0.9 Mach. 1 Mach is the speed of sound, which is 330 meters a second, which is 1/3. So 1/3 the speed of sound. Excuse me, it's 1 Mach is the speed of sound. So the speed, the velocity of the shadow across the surface of the Earth will be the orbital speed of the moon, which is 1 kilometer a second. So Mach 1 is basically 1/3 the speed of the shadow. So you can extend the duration of totality considerably by what they call eclipse chasing with an aircraft, an modified A320 aircraft flying at altitude. You can extend the duration of totality upwards of at least 10 minutes. If this eclipse lasted maybe 2 or 3 minutes, you can extend it by a factor of 2 or 3. If you, what they call chase the eclipse, you extend the duration of totality by that amount. So in the sun, we can an indication of solar activity is how many sunspots we observe on the surface of the sun. Clearly, we're still at a solar minimum. We're still in the solar minimum for this cycle, what they call the Saros cycle. Cycle of eclipses are categorized in what they call Saros cycles. Saros cycle is a series of eclipses. It occurs as a family of eclipses. Okay, in this particular Saros cycle, for this eclipse, the sun is very quiet. We're at a solar minimum. We're going to be coming out of a solar minimum very soon. Okay, we see no sunspots on the surface of the sun. Sunspot, as I described previously, is when the sun's right below the surface, the photosphere of the sun, the outer hot layer of the sun we call the photosphere, consists of a series of convection zones, where if you think of a room, when you turn the heat on in a room, the hot air rises, right? You turn the heat on, up towards the ceiling will be warmer, towards the floor is going to be cooler. All right, so that same effect is happening just below the surface of the sun, or the photosphere of the sun, in a series of convection cycles where the heat rises, is liberated away into space, and now that gas is cooler, it will subside back down into the internals of the sun, take more heat with it, and liberate that heat out to the surface in one continuous cycle. Now what happens, because the sun behaves as a fluid, it's a very, very powerful, and also has a very powerful magnetic field. That magnetic field sometimes gets bent over on itself or intertwined with itself, causing breaches in that convection cycle, which breaks the flow of energy to the surface. And when that happens, we have a sunspot. That sunspot appears cooler compared to the surrounding regions of the sun's surface, photosphere. However, it's still very, very hot. It's only a few hundred degrees cooler. But nonetheless, that's an indicator of the internal activity of the sun. Okay, the lower the activity, the more stable and quiet the sun is. We call that a solar minimum, and that has an 11-year cycle. From minimum to minimum, or maximum to maximum, is the solar cycle, which is 11 years. So every 5.5 years, we go from minimum to maximum. That length of time is about 5.5 years. Right now, as we look at the sun, We see no sunspots. We do see the limb darkening, as I described previously, where we're looking into deeper layers of the sun's photosphere and the superheated gas just below the surface. It looks darker because it's actually, we're looking into a thicker layer of the atmosphere, and subsequently that region of the sun will appear slightly darker compared to the central part of the sun. Okay, so that's limb darkening and the solar activity. I'm Dr. Jim Daly, your host for this live event with Astronomy for Change. astronomyforchange.org. If you're joining us live, we're watching the total solar eclipse of 14 December 2020, visible from Latin America. This is off the western coast of Chile. Right here. Okay, this is the 100-kilometer wide shadow of the sun. This is the umbral shadow and the penumbral shadow. The penumbral shadow, outside of the penumbral shadow, you don't see any eclipse. The eclipse has already passed, and please check back with us a little bit later when we post this video to our channel. You can see the eclipse in its entirety. A beautiful total eclipse of the sun. Beautiful coronal streamers, some mild solar prominences. A prominence is the jets of hydrogen gas that leap off the surface of the sun, off the photosphere of the sun. The sun is not a solid surface. It's a superheated, gravitationally bound ball of plasma, superheated plasma. That's 700,000 kilometers in radius, 1,500 kilometers, 15 million, 1.5 million kilometers in diameter, excuse me. It's 110 times the size of the Earth. So we could fit 110 Earths across the face of the sun here. Now, how does an eclipse work? Well, this is a new moon phase. We're a new moon phase. It's the only phase of the moon where you can see a total eclipse of the sun in the moon's 29.5-day cycle. Since the moon is 400 times smaller than the sun, but 400 times closer, it's a perfect geometric fit. Perfectly covers the face of the sun as the moon. And what are the odds of that happening? What are the chances that we'll have a satellite that's exactly 400 times closer and yet exactly 400 times smaller than our parent star? Pretty incredible odds. Well, that's what we have. I mentioned earlier that that we're trying to reproduce here on Earth the energy production that's ongoing inside the sun. 600 million metric tons of hydrogen are being transmuted every second of every day for the last 4.5 billion years since the sun formed out of a cold, self-gravitating cloud of gas in the interstellar medium to form our star. Ever since then, since the sun started burning bright in space, 600 million metric tons of hydrogen is being transmuted, synthesized into helium, producing the energy that's sustaining us on our planet. Well, that energy source, we've yet to reproduce that sustainably here on Earth in the form of a nuclear fusion reactor. There is an ongoing project in the south of France called ITER, I-T-E-R, and we have a story on our website, astronomyforchange.org, where we discuss ITER. ITER will go live, will be commissioned in about 4 years hence, around 2025, as a demonstration of nuclear production. And if the tests are successful, ITER will begin commercial production of nuclear energy in about 10 years following, or 15 years hence from now, in about 2035. That's if all the tests go well. And the technology is a proof of, ITER is a proof of concept reactor. If it works, we can sustain a nuclear fusion reaction for more than a microsecond or a millisecond. Then, see, the problem with nuclear fusion, is the amount of energy required to produce the reaction, and this is the break-even point. Right now we're below the break-even point, where the amount of energy put into the reaction is less than we get out of it. So there's no point in actually going forward with it. When we reach that break-even point or crossover, where we hope to get a 10 times, one order of magnitude or a 10 times greater yield of energy out than we do energy in, at that point it becomes a viable, sustainable energy source. And that's what ITER, the whole proof of concept idea of ITER will be. And hopefully we'll be able to do that, and we'll see in about 4 years hence. In about 2024, 2025 actually is when it's to be commissioned. We'll begin producing nuclear fusion power. There's no connection to the grid, since it's just a proof of concept. If it works, the demo model, that would be a demo model, then a production reactor, a commercial production reactor, will be produced in the 500 megawatt range. 50 megawatt input power to produce 500 megawatt output power through nuclear fusion. And if all goes according to plan with ITER, ITER, that will happen in around 2035. So we're still 10 to 15 years out before we have a sustainable, viable nuclear fusion solution for our energy needs here on planet Earth. And as the moon continues to move across the face of the sun, moves away, approaching fourth contact, we continue to see that the sun is a very quiet. There are no sunspots. And thus, we have to deduce from that we're in a solar minimum. The sun is very low solar activity. With the increase in solar activity, we have increase in solar flares. A powerful solar flare could have the effect of an EMP. The results of the effect of a nuclear blast produces an EMP, which basically shuts down all electronic communications, all electronic activities, all electronic equipment gets shut down by an EMP. A solar flare would have such an effect. Such an effect was observed in 1859 with the Carrington event, where just the budding technical age, when we're just coming into the Industrial Revolution, is just getting started. And we're just starting to produce our first telegraphs and our first power lines. The Carrington event, a very powerful solar flare, produced the effects of what we would see from an EMP, electromagnetic pulse. Basically shuts down all electronic activities, all electronic communications, any kind of power generation, that all gets shut down with an EMP, an electromagnetic pulse. So fortunately for us, during the solar minimum, the probability is very low that such an event would occur. And in our technical age now, we rely very heavily on technology, electronics, all that which gets shut down in an instant with a solar flare, an X-class solar flare that would impact the Earth, would temporarily cripple our advanced technical society today in the form of what could be considered an EMP, the effect of an electromagnetic pulse. Again, I'm Dr. Jim Daly with Astronomy for Change. This is a live feed from the west coast of Chile in South America. bringing you the total solar eclipse of 14 December 2020. Our live feed is courtesy of Reuters, hosted here at astronomyforchange.org. I'm Dr. Jim Daly, your host for today's live event. Now, as we saw earlier, the birds, thinking that we have a change of, we're coming into twilight, begin their end of day rituals and the activities that they go through it towards the end of the day when the sun starts setting, it gets darker. The birds change their behavior, believing that the day is closing, when in fact we're just going through a total eclipse. And it's understandable how the ancients, not understanding what's actually happening, could attribute a deity to this. The sun god, or the Chinese mythology, had a giant dragon taking a bite out of the sun. Now, I should mention also that the geometry of our solar system is one of the things that allows the eclipse, allows us to witness an eclipse. The fact that the moon is 400 times smaller than the sun, but yet 400 times closer. And since all objects in the solar system orbit in what we call the plane of the ecliptic, which can be described by the path of the sun across the sky. Basically, if you look out over the solar system, all the planets orbit in a particular plane, within a few degrees of that particular plane. That plane we call the plane of the ecliptic. Those solar system objects also include the moon. Even though the moon is inclined, the orbit of the moon isn't perfectly aligned with the plane of the ecliptic. It's 5 degrees inclined to the plane of the ecliptic. So that's why we don't see an eclipse every month at the new moon phase, which is the only phase of the moon that we get to see an eclipse, when the moon perfectly passes in front of the sun. In about another 10 or 15 minutes, we'll be arriving at fourth contact. Fourth contact is when the eclipse completely ends. Those of you who are just joining us now, we can go back to, I'll show you the map briefly. Here, eclipse begins out in the middle of the Pacific here. Here's the Hawaiian Islands. Eclipse begins here. Okay, that's the penumbral shadow. Here's the umbral shadow here. Here's the penumbra. Out here, if you're outside of this region here, you don't see any eclipse at all. So the North America here, this part of the continent of the Americas, we don't see any of eclipse. Mexico and the northern parts of here, right there. So the diameter of this small circle here is the path of totality, where it's traveling across the surface of the Earth at the orbital speed of the moon, which is 1 kilometer per second, or 1,000 meters per second. The speed of sound at the surface of the Earth at sea level is 330 meters per second, which is more or less one-third the speed of the shadow. So if you were in an aircraft that's flying at like 0.9 Mach, 1 Mach is the speed of sound, which is 330 meters per second, you're flying at 1/3 the speed of the shadow of the eclipse. So you could follow the eclipse or chase it and extend the duration of totality. Colleagues of mine actually do this. They've actually modified an A320 aircraft, where the aircraft is modified to allow instrument bays, photographic equipment, telescope equipment, and so forth. The aircraft flies at altitude, at cruising altitude, and chases the path of the eclipse here, and extends the duration of totality by up to 10 or 15 minutes, and in some cases longer. Okay, so the eclipse ends off the west coast of Africa, over here. Here's a 3D animation. Okay? It's just egress, totality egress on the western coast of Chile, and this is the eastern coast of Argentina, and the eclipse ends off the western coast of Africa over here. Okay? Here, this is a guide or a legend here of what you would see if you were down here. Anything in the white, you see no eclipse at all. In the light tan, you see 30%. 40% is this region here. 90% is here. 100% is here. Anything inside here, this is the path of totality. The central 100 kilometers right there. Okay. Let's go back here. Right here. Okay, this map here, if you're inside this, these boundaries here, you get to see a total eclipse. This is what they call the center line, where you get to see maximum eclipse. All right? This region here defines the region of totality. If you're inside within this blue boundary here, you get to see the total eclipse of the sun. Here's the western coast of Chile. Here's Santiago de Chile. It's the capital of the country here. Okay. Temuco, the northern border of the band of totality, just touches on the city of Temuco in Chile. Los Angeles de Chile. Star Key is here. Santiago de Chile is the capital up here. Okay, let's go back to our eclipse feed. Okay. Now clearly you have to have a filter in front of your telescope. I don't believe at this point this is not a telephoto. I believe this is a telescope. The image scale is too big to be a telephoto lens. It's my belief that this is a telescope, a telescopic view of the eclipse, or a very, very long telephoto lens with a filter. It's more likely a telescope. We're approaching fourth contact, where the trailing edge of the moon will touch the leading edge of the sun, and the eclipse will end. It's about 15 to 20 minutes. Thank you for joining us today, for those of you who are here. If you're just joining us now, I'm Dr. Jim Daly, Astronomy for Change, your host. We're witnessing live total solar eclipse in Latin America off the western coast of Chile. Courtesy of Reuters news agency. Live feed courtesy of Reuters. You have a smaller image. Oh, maybe this is a zoom lens. This is zoom lens. So they got a small image here. This is a zoom lens. Here we go. It's a zoom. Based on the image scale, this is a 600 millimeter zoom. So the ancients believed that the ancient Chinese mythology had a dragon taking a bite out of the sun. Okay, the ancients had similar mythologies about before the understanding that on the heliocentric model of the sun is placed at the center of the solar system. All the planets in orbit around the sun. Everything orbiting in the plane, we call the plane of the ecliptic, where since all the objects in the solar system, well, most objects, all the large or the major bodies that include things like moons and all planets, orbit within a few degrees of this, what they call the plane of the ecliptic, or the apparent plane with the sun at the center, in which, if you can imagine in 3 dimensions, all the planets orbit inside this plane. Now, the moon orbiting the Earth is not perfect. Its orbital plane is not perfectly aligned with the plane of the ecliptic. It's off by about 5 degrees. Consequently, we don't see an eclipse of the sun every month at the new moon phase. Okay? In fact, there is a total eclipse of the sun every month, occurs every month, but many times the focus of the shadow, or the moon's umbral shadow, is in space above or below our planet. It's not always going to be on the surface of the planet, but there is an eclipse of the sun every month at the new moon phase, but we just don't get to see it. Eclipse of the sun occurs approximately once every 18 months. All right? If the inclination of the moon's orbit, if the moon's orbit was inclined perfectly with the plane of the ecliptic, or the path of the Earth as it orbits the sun, we would see an eclipse of the sun every month at new moon phase, when the moon comes exactly between the sun and the Earth. The sun is 400 times further away, yet 400 times larger than the moon. Hence, as a perfect geometric cover, the moon perfectly fitting across the face of the sun. All right? The sun's energy comes from fusion of 4 hydrogen nuclei, proton, transmuted every minute, every second of every day for the last 4.5 billion years, since the sun began to burn bright in space, the result of a gravitational collapse of the cold gas and dust in what we call the interstellar medium, the space between the stars, which is filled with cold gas and dust, comes together through self-gravitation. Eventually, over time, a long enough period of time, the internal temperatures reach a point where nuclear fusion reactions begin, converting hydrogen into helium, where we have the output of that reaction as a gamma ray, which is the highest energy form of electromagnetic radiation. Visible light, we see the universe around us. Invisible light, gamma radiation, or gamma rays, is the highest form of electromagnetic radiation. Highest energy, I should say, of electromagnetic radiation. That's the product of this nuclear fusion reaction, where we call the proton-proton chain, where we have protons coming together to form. It's a 3-step process where we have 2 protons come together, 4 in 2 separate lines, 2 separate parallel reactions. We have 2 protons come together in tandem, in parallel, with a result of 4 protons. 2 of them become neutrons. They liberate these tiny little particles called neutrinos, which take away some of that energy and maintain the charge, because we have to conserve charge. And we have 2 protons, 2 neutrons, and then in a more temperate environment, where we don't have the superheated temperature of the sun internally at 15 million Kelvin, we'd have a stable helium atom with 2 electrons electrically balanced perfectly the 2 positive charges of the proton. We have a stable helium atom. Right now, inside the sun, they're producing alpha particles. An alpha particle is another name for a helium nucleus. We have 2 protons, 2 neutrons being produced. 600 million metric tons of hydrogen is transmuted into helium every day, has been doing that every second of every day for the last 4.5 billion years, and will continue to do so for at least that many more years henceforward, where at that point the hydrogen runs out and the sun then goes through a series of changes. Internal dynamics change. The sun begins to expand, collapse, starts to heat up again. We'll start to use the helium as a nuclear fuel, and we'll enter what we call the helium burning phase. It will will expand and then shrink a little bit, maintain some stability for about 100 million years in its helium burning phase, where it will produce carbon and oxygen through the transmuting in a 2-step process called the triple alpha process. We'll take 3 alpha nuclei, which is a helium nucleus, to produce carbon. The helium nucleus has an atomic mass of 4, we bring three of those together, we're going to get a carbon-12, and that's where we get carbon. The only way to produce carbon at all, anywhere, is through the triple alpha process in the cores of stars. So the next time you pick up a pencil and write a note, or fill in a bubble form, whatever you use a number 2 pencil for, try to remember that the carbon in that pencil came from the inside of a star. Okay? Right now, well, that's not happening yet in the sun, but that will happen when the sun starts to evolve away from that phase, what we call the main sequence phase of its, right now, where it's in what we call in hydrostatic equilibrium, where the outward pressure of the gas pressure is being balanced by the inward pull of gravity, and we have a stable situation. That's called hydrostatic equilibrium. But that will change when the hydrogen, the complement of hydrogen inside the sun, begins to dwindle down to a point of 12, where it's only 12% of what it started with 4.5 billion years ago. When that happens, the sun's internal dynamics change, and it will begin to expand and then collapse again, contract again, but will stabilize when helium fusion begins, producing carbon and oxygen. When you add another alpha particle to a carbon nucleus, you're going to get an oxygen nucleus, which is atomic mass of 16. And then, so the triple alpha process will produce carbon and oxygen. It will be a helium fusion cycle. The sun is nowhere near that. We do see stars in our sky tonight, in the winter sky, stars like Betelgeuse in the right shoulder of Orion. His right shoulder is the star Betelgeuse, which is an evolved red supergiant star in a helium burning phase, where that star is using alpha nuclei in a triple alpha process to produce carbon and oxygen. That's how that star is deriving its energy. And it will continue. That will end. The helium will get consumed, and it will then start to use the carbon and oxygen. Will fuse carbon and oxygen, produce magnesium. Then we have a magnesium burning cycle. Then we're going to have an oxygen burning cycle. Then a silicon burning cycle. At that point in the silicon burning cycle, which lasts 24 hours, it will produce all the heavy metals up to and including iron and nickel. And that's the nuclear dead end for all stars. And when you try to add an alpha nuclei to an iron nucleus, you take energy out of the system, the stellar core will chill, literally chill. And since we lose the outward gas pressure, the outward pressure suspending the star from its inward collapse from gravity, that ends in an instant at about 3/10 the speed of light. The whole thing will just implode in on itself, rebound off that core in one of the most spectacular events in all of nature, a type 2 supernova. That only happens for big stars like Betelgeuse. That never happens for our sun. Our sun will basically just go quietly into the night, as what they call the end stage for the sun will be something what they call a planetary nebula, with the remnant at its center called a white dwarf star, no longer producing energy but still very hot. And the ionizing radiation from that white dwarf star will cause these beautiful colors we see in these things we call planetary nebula, which have nothing to do with planets. They just, in a small telescope, they look like planets with their shape. They're round, they're spherical, they're very pretty colors, blues and pinks, things like that. So they called them, the astronomers 200 years ago called them planetary nebulae because they look like planets, have nothing to do with planets. Okay, see, we have a smaller image of the sun. They zoomed out. We're approaching fourth contact, where the limb of the moon will egress completely off the limb of off the sun's face, and the eclipse will have ended. Okay, so there you just got a crash course in stellar astrophysics, courtesy of Dr. Jim Daly, your host here today at Astronomy for Change, astronomyforchange.org, where we're streaming live the total solar eclipse from the west coast of Chile in Latin America. Our thanks to Reuters News Agency for providing the live stream. Now you might ask, well, what about the rest of the periodic table of the elements? Dr. Daly, what about everything heavier than iron and nickel? What about those? Well, when the star explodes, the release of gravitational potential energy, which is what this is, all that gravity that was holding that star together now is unleashed in an instant. Okay, that release of energy then takes the neutrinos, the free neutrons that are flying around in this cacophony, this maelstrom, this stellar maelstrom. There's no electric repulsion, and those neutrons then can combine with the metals that have formed the heavier elements like hydrogen, like nickel and iron, to form everything up to uranium, which is the heaviest naturally occurring element in the periodic table. So that's basically how we get. People often ask me, well, what about the rest of the periodic table? Beyond uranium, any elements heavier than uranium, the actinides, they're synthesized in the lab. They don't occur naturally. What do we see here? What is this? They're taking the filter off the camera, it seems like. This is the surrounding region. You can see, yeah, I know what they did here. Here are the mountains. Here are the buildings in here. You notice that the lighting situation is more or less normal because the eclipse is almost over. There's clouds in the distance here, fog and clouds in the distance. This is the country of Chile, courtesy of Chile. The word is news agency in Chile. I'm not entirely sure what city this is in Chile. It's the clouds in the distance. And you notice the daylight conditions. Here we are. Still somewhat subdued, the lighting conditions. But it's almost over. The eclipse is going to be coming to an end pretty soon. At fourth contact is the point in time. Here's a dramatic view here, looking towards the coast. Overcast conditions here. You can see the overcast conditions here. The tide this is low tide, apparently, which would be consistent with the phase of the moon. Being a new moon phase, this is consistent with the phase of the moon. You have the low tide. You can see the waves are breaking way out here. Okay, you see the shoreline here. This is low tide. This is consistent with the phase of the moon. As we know, the tides are regulated by the gravitational interaction with the moon and the Earth. The gravitational interplay between the moon and the Earth, gravitational interaction, the gravitational interplay between the Earth and the moon is what creates the tides. And I believe they've taken the view away from the sun because it's overcast and we don't see any shadows. If the sun was still visible, although you can see shadows here, these people standing here, the sun is directly overhead because this shadow is directly below them. Okay, these individuals walking here to the left, observe their shadows, you get a sense of where the sun is in the sky. It's more or less directly overhead. So apparently fourth contact is either already happened or it's approaching. We can't tell. I believe he took the filter off the front face of his camera, and thus we see the scenic view here. I'm Dr. Jim Daly with Astronomy for Change, your host, astronomyforchange.org. Having brought to you this the total solar eclipse, 14 December 2020. All right, friends, thank you for joining us. Don't forget, a week from today, the 21st of this month, is the winter solstice, the point during the year when the sun is at its lowest point in the northern hemisphere. Down here in Chile, it's their summer solstice. For us, it's our winter solstice. It's their highest point, the sun in the sky. For us here in the northern hemisphere, it's our lowest point in the sky. Next Monday, a week from today, we're also going to be witness. We put a video up on our channel, on our YouTube channel. We're going to be witness to a conjunction of the large planet, the giant planets Jupiter and Saturn, in the southwest, towards the following sunset. Look to the southwest, where the giant planets Jupiter and Saturn will appear to come together and merge in the sky as one object. Now, the University of Exeter in the UK, and you can get all the details on our previous video that we have on our channel about that event. Let me see if I can find it. Yeah, I'm going to. JupiterSaturn2020.org is the website. Sign up. We're going to be hosting this event live as well next week. Please stay tuned. Come back for the actual time and date. The actual time when we're going to be going live. We're going to put the scheduled event up on our YouTube channel. So we're going to stream this event live next Monday, a week from today, on the occasion of the conjunction, which won't be visible again for 60 years hence, in the year 2080. So if you want to see such an event again, you're going to have to wait 60 years. So we're going to be streaming this live, courtesy of the University of Exeter in the UK, next Monday. And the event will be scheduled on our YouTube channel, so please stay tuned for that. In any case, thank you for joining us for this live event, and hope to see everybody again soon. The great philosopher Plato famously said, "Astronomy compels the soul to look upward and leads us from this world to another." Astronomy for Change is a non-profit organization whose mission is to effect positive change through astronomy and science education. It is our belief that by inspiring and empowering current and future generations to become interested and engaged in astronomy and science, this positive change will be realized. If you found this video helpful and educational, please like, subscribe, and share. Also, why not consider supporting us on Patreon? Head over to our homepage, astronomyforchange.org, click Support Us via PayPal or Patreon, and head on over to our Patreon page and choose a membership level suitable for you. Every little bit helps us produce the great content and further our mission. Also, why not consider becoming a member? Membership is free at Astronomy for Change. Head on over to our homepage, choose the membership link here, click it, put your name and your first name and your email, and you'll be added to our list. You'll receive a comprehensive digest of all our videos and articles and all our great content. Joining and becoming a patron, helps us grow and improve and more fully realize our mission. Thank you. This is Dr. Jim Daly for Astronomy for Change. Until the next video, please stay well and keep looking up.